Hello, and welcome to NASA's Jet Propulsion Laboratory in Southern California. JPL is the home of NASA's longest continuously operating mission, the Voyager mission. The Voyager mission is celebrating a historic milestone right now, 45 years of flying through space and collecting science data along the way. And since it's been on this 45-year-old journey, the Voyagers are actually also the most distant human-made objects out there. I'm Jaree Cook with JPL's Digital News and Media Office, and I am here with a full-size model of Voyager. So there are two Voyager spacecraft, and they look just like this. So right now, we're right in between the two launch anniversaries. The first Voyager launched on August 20th, and the second Voyager launched on September 5th. And so we're here today to talk to you some more about Voyager, and I've got two extremely knowledgeable guests about the mission. The first speaker is going to be Linda Spilker, the Deputy Project Scientist, and then we're going to have a propulsion engineer, Todd Barber, to talk to you today. So we are going to take your questions. So if you're online now, you can drop your questions in the chat or in the comments box, and we will try to get to as many as we can. All right, so let's start with Linda. Come on over here, Linda. I'm really excited to talk to Linda because she's been with the mission a long time, actually got her start in her career with the mission. So welcome, Linda.
It's great to be here, Jaree.
Yeah, I'm excited to have you here. So why don't you catch us up? Where have the Voyagers been and where are they going? And actually, where are they right now?
Well, both Voyager spacecraft have been out in space since 1977, and they flew by the 4 outer planets. Voyager 1 and 2 flew by Jupiter and Saturn, and then Voyager 2 continued on alone to Uranus and Neptune. And only Voyager 2 has flown close to Uranus and Neptune so far. And then there are about 2 decades where the Voyagers continued on past the planets toward the edge of this bubble where the solar wind pushes out, meets with the interstellar wind, and forms what we call the heliosphere. In fact, if you look at this graphic, Jaree, you can see that giant bubble. It's moving through space like a comet. You can see the 2 Voyager spacecraft toward the nose of that bubble with the tail going out behind. And in interstellar space, they're measuring what you would see from explosions from supernova. And Voyager 1 is about 15 billion miles away from the sun. And for comparison, that's about 150 times further away from the sun than the Earth. And Voyager 2 is about 12 billion miles away.
Yeah, so they're extremely far away, and yet they're still operating. So why are scientists so excited that the Voyagers are still operating after 45 years?
Well, Jaree, with this spacecraft, let me just point out there are 3 instruments here covered in their black thermal blankets. These are the particle instruments, and that's part of the package. And so the particle instruments are measuring the cosmic rays, those high-energy particles that are out in space. And that shield, that heliospheric bubble, protects us from a lot of those cosmic rays. We're also looking at the magnetic field. So far, the sun is controlling the direction of the field, and we're waiting for it to turn into the direction of interstellar space. And even some of the biggest storms on the sun produce waves that cross through that boundary and can be measured by Voyager. So it's a very exciting time for the scientists.
Yeah, so it's exciting now, but it's also been exciting throughout its journey. I know you have a long history with Voyager, so could you tell us about some of your most meaningful moments?
Well, I think for me on Voyager, one of the most meaningful moments was to be there on August 20th for the launch of Voyager 2. And that launched my career. I was just fresh out of college, and it was great to start my career and start the Voyager mission at the same time. And if you look at this next picture here, the person seated, that's me back in 1979, talking about what we were going to do with the Jupiter flyby, in particular the Voyager 2 Jupiter flyby. And one of the things I really liked also was that at Jupiter, one of those tiny moons, Io, had active volcanoes going off. In fact, I have a button here from the Voyager 2 flyby, and you can see a volcano in blue going off on the surface of Io.
Yeah, and you were mentioning to me before that you would bring your sleeping bag in. I mean, what was it like, waiting for all that data to come back?
Well, it seems like some of the best data would come back in the middle of the night, and we'd have a list of when those pictures would come back. And so we'd bring our sleeping bags and get a couple of hours sleep in between some of the best and newest pictures. I remember staring at the screen, watching line by line as each of those pictures came back, knowing I was seeing for the first time some of these worlds that were pinpoints of light in telescopes, and now were worlds in their own right. So exciting. Didn't want to miss a moment of it.
Thank you, Linda, for sharing what it was like to be in the room where it happened, right? It sounded really exciting. So I'm going to thank you, and I'm going to bring on our second guest over here. So Todd, why don't you come over? Thank you, Linda. We'll come back to Linda in a little bit with some questions, and I want to remind you, if you've got questions now, drop them in the chat or in the comments box, and we'll get to as many as we can. So Todd, I'm excited to talk to you because for Linda and the other scientists to get their data, we have to have a team of engineers flying the spacecraft taking care of it. So I know you're a relative newbie to the team. So what does it mean for you to join the Voyager team?
Oh, it means the world to me, Jari, and thanks for having me today. I remember being a nerdy little kid in Kansas, 13 or 14 years old, and seeing the pictures that from the mission that Linda was describing when she was there doing the real work. I got to see these images in National Geographic magazine, which you can see on your screen now. And I remember those covers just like it was yesterday, even though that's been some time ago. And I dreamt of one day, I became hooked for life in the allure of planetary science. I knew it was my destiny. I never dreamed that I'd get to work now 32 years and counting, my only job at JPL, but let alone in 2022. If you'd have told that kid in Kansas in 1981 that in 2022 he'd be one of about a dozen engineers getting to fly these two 45-year-old spacecraft, he would never believe it. So just delighted to be here today and try to keep the spacecraft alive.
Yeah, and so it's been great that you've been able to personally come full circle, but you know, these spacecraft are vintage, as you say, and so I was wondering if you could talk to us a little bit about the challenges of flying these spacecraft that have been through so much already.
Yeah. How much time do we have? Just half an hour? Well, it's kind of like keeping an old car running. They are geriatric spacecraft by NASA standards, and it's been the hardest engineering I've ever done in my entire career, but also that means it's the most fun, because engineers love a challenge. We lose 4 watts a year on the spacecraft. Things are insanely cold. The propellant lines are about to freeze. We've had computer chip issues, and I'm delighted to report we had a problem with the spacecraft in March or April that really flummoxed us. Our attitude control telemetry was nonsensical. We couldn't get any health and safety information about the pointing of the spacecraft or any of the thruster operation, and we just announced today we've fixed that problem. So it's just a tremendous testament to the brilliant engineers I work with.
Yeah, fixing it from 15 billion miles away.
Exactly, the ultimate telesurgery there.
Yeah. Okay, well, we're going to now turn to some questions, and so I'm going to invite Linda back up here on the stage. All right, so again, if you've got questions, you can drop them in the chat, and we'll get to as many as we can. They're coming in right now, so I am going to ask Todd the first question. Electro Bard on Twitter asks, did you design the probe to last this long? What subsystems surprised you at their longevity and which failed before you expected them to?
Electra, that's a great question, thank you. So we actually barely were able to design this mission to last 5 years, which was the requirement to get to Jupiter and Saturn and get the data played back. And at the time that was already a stretch goal for NASA. But when people had a chance to use that slightly better part or build the mission for longevity, they did so, in the hopes that maybe we'd get to 12 years, because then you could get the Uranus and Neptune flybys with Voyager 2. I don't think anyone could have possibly dreamt we'd be here in 2022 with two 45-year-old spacecraft still going. I've mentioned some of the problems we've had along the way. We had some early failures. The radio receiver on one of the spacecraft failed within the first day. So we've had to use a few backup systems here and there. Personally, I'm most excited about the thrusters. We have a prime branch, a backup branch, and both of those have seen degradation. And ordinarily, that would be the end of any mission. Good old Voyager had another trick up its sleeve. Underneath the spacecraft, there's a third set of thrusters called TCM thrusters, trajectory correction maneuver thrusters. And we've actually been able to use those to control pitch and yaw on Voyager since about 2018, 2019, for both Voyager 1 and Voyager 2. Never really designed to do that, but some genius thought, let's write the software just in case we have to do that. We turned on those thrusters for the first time in 30 years in Voyager 2's case, in 37 years in Voyager 1's case, and they started right up and have been controlling pitch and yaw ever since.
Yeah, and so the TCM thrusters, they were actually used for the planetary part of the mission, right?
They were, yeah. Long before I joined JPL or even dreamed about the chance of working on Voyager, those thrusters did the lion's share of the work we took advantage of this 176-year extremely rare cosmic alignment to get all 4 gas giant outer planets. But even then you needed those thrusters to fine-tune the trajectory, to patch the sections together to get from Jupiter, Saturn, Uranus, and Neptune. So they had their heyday and were basically done by 1989. But of course, never count them out. We need them here in the 2020s to keep going with the mission.
Yeah, I know that sometimes you've said, Linda, expect the unexpected with Voyager, right?
Absolutely. There are always surprises around the corner. When you think you have all the answers, that's when you get your biggest surprise.
Well, I have a question for you now, Linda. Okay, so Sea of Stars on Twitter asks, and we get this question quite a bit, is there a possibility of either probe turning its cameras back on after all that time and take one last image of our solar system again before they can no longer produce enough power? And what would that view of the solar system even look like?
Well, it turns out we just don't have enough power to turn the cameras back on. In fact, the Voyager 1 cameras went off in 1990, but before they did, on Valentine's Day, they took this wonderful portrait of the solar system with individual shots of planets, including a view of Earth. If we could turn the cameras back on now and look back at our solar system, it would have shrunk down to something that's quite small. And our sun is starting to look like one of the ordinary stars you might see at night. It's still brighter, but it's getting close.
Thank you. Yeah, and I know that one of the last pictures it took was that pale blue dot image of Earth. Do you want to talk about that?
Yeah, it was really an interesting and spectacular picture. In looking at the pictures, it was kind of hard to find some of the planets. And there was the Earth in what looked like a sunbeam, some scattered light from inside the cameras. And Carl Sagan coined it a pale blue dot because it's all the life that we know of in our solar system is on that one tiny world, and how special that world is.
Thank you. All right, I'm going to turn to Todd again because, Todd, I know you love math.
I do.
So we have a question about a light day. So a light day, explain that to our audience here. But Mad Mark on Twitter asks, when will you be a light day away from Earth?
That's a great question. And so we've talked so far about billions of miles, and that's a great way to realize just how far away these spacecraft are. Another way to talk about is in terms of the communication delay in either sending a command to Voyager or getting something back. And that's using radio waves that move at a zippy 186,000 miles per second, the speed of light. So the moon is about a second and a half, Mars a few tens of minutes, Saturn maybe an hour and a half. Voyager 1 is 22 light hours away. So if we send the data from Voyager 1 is 22 hours old, and to send a fix if there's a problem, for example, would take another 22 hours. So Voyager has to take care of itself for 2 days. That number keeps increasing, and I did the math, and it's November of 2026 when Voyager 1 reaches 1 light day from Earth. So I think we should celebrate that right before the golden anniversary in August and September of 2027.
Yeah.
But lest we think we've gone a long way, the nearest star is 4 light years away. So even after 50 years, we're only 1/1500th of the way to the nearest star.
Yeah, that's amazing. The sense of scale is a little different where the Voyagers are than here. Okay, I got another question for you, Todd. Okay, so AKA Sai on Twitter asks, what would you do differently for a next-gen Voyager mission to make the spacecraft last longer, go faster and further, and collect new types of planetary and interstellar data?
Wow, that's a great question. I don't think I'd change much of anything as far as the longevity goes. Maybe a few more redundant systems if you could afford the mass to do so. I would leave to Linda as far as which science instruments she would like the next generation Voyager. By the way, the planets will align again in 2153, so I hope we do at least a Voyager tribute mission then.
For Voyager.
Another chance. And as far as the, what was the third part of that, or the middle part of that question? I wanna make sure
to go faster and farther?
Faster. Yeah, so again, the cosmic alignment of the planets there is extremely rare, the 176 years. There are other more exotic forms of propulsion that, in theory, could get us to the outer solar system faster. And I know NASA's looking at that, and I would love to see that within my lifetime, too. Otherwise, it takes a really long time to get to the outer solar system.
Yeah, an entire lifetime, in fact. Okay, well, I'm going to ask a question to Linda here. Okay, and I'm going to ask you this because you were actually around in 1977 when Voyager launched. So Coyote Siege 92 on Twitter asks, did anyone think in 1977 that you'd still be hearing from Voyager 45 years later?
I can say in 1977 at the launch, no one was talking about where Voyager would be in 45 years. And in fact, when you look at where the Voyagers went, out the nose, that's the closest point to the heliopause. And it was just luck we happened to go out that direction.
Okay, well, yeah, because it could have gone out the tail and then maybe...
We'd still be in the heliopause. Yeah.
Okay, well, I'm going to ask this first to you, Linda, and then I'll ask you, Todd. So Henry on YouTube asks, what college major do you guys personally think gets us the best chance at earning a job in these fields? And what majors did you study?
Well, Henry, that's a good question. I was a physics major pretty much through for my bachelor's and master's, and then got a geophysics and space physics degree. But certainly to be a scientist or an engineer, science classes are great, physics is really great, advanced math. Those are the kinds of classes that would prepare you, say, for a job at JPL.
Great, and what about you, Todd?
Yeah, I have bachelor's and master's degrees in aerospace engineering from MIT. And what I've found, though, at JPL, if it's a science degree or an engineering degree of any sort, we probably have a place for you here. I mean, as an example might be civil engineers that learn how to build Martian habitats using Martian soil. We have navigators and mathematicians. Biology's a big thing, looking for life outside of planet Earth. So you wouldn't think necessarily space travel would involve the biological sciences. But really, any STEM kind of background, there could be a position here at JPL.
Yeah, there's been lots of different, I've met so many people who've started one way and did other things. I know there's people who've worked in even pharmaceuticals, and then they came and did sort of astrobiology here. So, okay, let me ask you another question, Todd, and if you don't know this, then I might ask you, Linda. How many years did it take NASA to build Voyager? Oh, and this is Priyanka on YouTube.
Okay, yeah, I will defer that to Linda.
Okay.
Yeah, I'm not sure exactly how many years. I think the concept really got started sort of in the late 60s. The opportunity was available. And I know that Ed Stone became project scientist in 1972, so I'm sure they were hard at work building Voyager in the 70s.
It's safe to say that we were lucky, extremely lucky, because probably 5 years earlier, 10 years earlier, we wouldn't have had the technology to take advantage of this 176-year opportunity. So we'll take a bit of luck whenever we can get it too.
Yeah, and one of the things that made Voyager last so long was that you guys did a lot of redundant systems, right? So that you had backups. So I imagine you wouldn't just build one thing, but you had to build two, right?
Right. All of the computers are redundant on Voyager. And we knew from an earlier flyby of Pioneer going by Jupiter that Jupiter's radiation environment was quite harsh. So we did a lot of things to radiation harden the two Voyagers, and that stood them in good stead not just for their Jupiter flybys, but now in interstellar space, where those cosmic rays or high energy radiation is greater, that extra little protection is at work still.
Okay, I'm going to ask you another question, Linda. So Spiderweb on Twitter asks, how much further will each of the Voyagers have to travel on their present trajectory until they're closer to another star than our sun, and how long would that take? We mentioned that the closest star is about 4 light years away, but of course things are moving in space, so how much farther is it?
That's right. Things are moving in space, so in about 40,000 years, each of the Voyagers in about 40,000 years, each Voyager will come within about 2 light years of another star. And so that's like half the way to Alpha Centauri now, but things are moving in space. And so 40,000 years, if there's anybody around, maybe they'll take a look and find the golden record.
Well, since you mentioned the golden record, let's actually talk about it. I know we have a picture up close of its cover. And so the golden record is this kind of time capsule of sounds and images, from basically 1977 or thereabouts, as a way to kind of, share with whoever finds Voyager someday, where did it come from? So I wanted to ask you both, what's your favorite sound on the golden record?
I think my favorite sound on the golden record is Chuck Berry singing Johnny Be Good. And the reason I really like that is that after the Neptune flyby, all the planetary flybys are over, we had a great big party out here in the mall at JPL. And Chuck Berry came and he played that song. And I think it's been my favorite on the record ever since.
That sounds like an amazing party. And what about you, Todd?
Well, I love the golden record very much. It's the most eclectic set of music you'll hear from every corner of planet Earth. But I think my favorite would have to be any of the Beethoven works on the record. He's the most represented composer, if you will. And I'm a pianist, and my piano teacher's teacher was Beethoven. So we played a lot of Ludwig, and it's nice to see we're sharing him with interstellar space too.
Yeah, I hope they appreciate the piano there. Okay, I have a question for you, Todd. And Greg on YouTube asks, how are you and the Voyagers able to communicate? Is it a pinpoint signal, or are you casting a wide net in both directions?
Oh, that's a great question. Well, at these distances, the radio transmitter on Voyager is about 18 watts, so it's less power than the light bulb in your refrigerator. So if you can imagine how that signal is attenuated, how much tinier and fainter it is once it reaches 15 billion miles away. We need giant antenna on Earth as part of NASA's deep space network to pick up that faint whisper of a signal. Now, because of that, we need a very directed signal within, fractions of a degree. Our high gain antenna needs to be pointed right at the Earth to be able to receive data and to transmit it back to Earth. And that's where we were so flummoxed with losing our attitude control telemetry, because we had no information on the pointing of that antenna. But we knew things were working because we were still getting a signal. We didn't have the details. And I'm happy for Linda's sake and her fellow scientists that the science data kept flowing that whole time. It just was very frustrating to the engineers not having that data until now.
Yeah, and I've heard that the signal coming back from Voyager is really weak too, right?
It is, and that's why one reason we need these huge antenna. They're up to 230 feet in diameter just to pick up that faint whisper of a signal from space. So it's both the size and the power of the antennas on Earth and the precise pointing that allows us to continue to monitor and talk to a vehicle so far away.
Yeah, well, okay, I got another question now, this time for Linda. So David Johnson on YouTube asks, what were the most surprising results you received from either or both of the Voyagers?
Well, I think surprising results for the Interstellar mission, being in interstellar space, have to do with directly measuring the cosmic ray abundance and seeing how they change. And as I mentioned earlier, the fact that the magnetic field hasn't rotated into the direction of interstellar magnetic field yet. The fact that the waves from the sun actually go out into space and beyond. But if you look back on the planetary flybys, I think Voyager really reshaped how we think about the moons themselves, and perhaps that some of these worlds might have liquid water oceans underneath their icy crusts that might be habitable. And so it's really to Voyager's credit that we found that moons don't just look like our moon. They can look like all sorts of different objects.
Yeah, and I think the Io thing was a surprise too when you found it, because it was actually in the navigation data, right? I mean, it wasn't even necessary. It was, was at the end of a day or something. Do you want to tell us a story about how those Io volcanoes were discovered?
Right. Well, it turns out we needed to take what we called optical navigation frames, where you would get sort of stars in the background to help you're pointing at these targets. And one of those frames had this fuzzy bump on the limb. And so I had to rule out, could it be like a bright galaxy? Could it be another moon peeking out from behind Io? And it turned out you rule out all those probabilities, and suddenly it's something coming from the surface of Io. As we started to look more closely, we noticed areas that looked like volcanoes, and they were erupting even as we could see them in the Voyager pictures and forming this ring of where that lava came back down. It was just incredible. And then Neptune's most distant moon, Triton, it also had geysers, and that was a complete surprise. So far from the sun, so cold, and yet these little tiny black wisps coming up from the surface of Triton. So many surprises with Voyager.
All right, well, I'm going to ask you another question, and maybe you can take this as a more general one, even to just explain, you know, the directions the Voyagers are heading. But Bruce McNinch on YouTube asks, have there been any unexplained changes in speed or direction for either of the Voyagers?
Aha, in other words, have we flown close to something that perturbed us a little bit? Well, so far, to the best of our knowledge, no, there's nothing that's happened to the Voyagers that have changed their speed or direction in an unexpected way. If you fly close to a large gravitational mass like a planet, that would bend your trajectory, and that's what we did early on in the mission. So far we haven't seen anything, but who knows what's out there.
Yeah, and the reason that we kind of bent upwards and bent lower is because there were certain things you guys wanted to see on the planetary voyage?
Right. Well, with Voyager 1, we wanted to go close to Saturn's moon Titan. And in doing that, it bent us out of the plane of the planets, bent us upward. And with Voyager 2, we wanted to fly very close to Neptune's moon Triton. And so to do that, we flew over the pole of Neptune and down to catch Triton, and then kept going out of the solar system that way.
Great. Okay, I'm going to ask one last question to you, Todd. Okay. Travis Winch on YouTube asks, keeping the probes online is one thing, but how do you maintain the ground systems that could be as old as the probes, or are all the ground systems completely modern?
Oh, Travis, that's a great question. And it is a real struggle. You know, as you can imagine, back in the days when Voyager was launched, it's punch cards and tape drives and things like that. So we have struggled with that. We've also done a number of spacecraft moves, you know, from off the JPL facility back on, and inevitably some problems might pop up during these transitions just to keep these old systems running. It's useful to have some people that understand assembly language and the old code too. But yeah, it's definitely one of the major problems here that we have to deal with on Voyager to keep getting data in the 21st century.
Okay, all right, well, let's see. I think we're going to wrap it up here because I think this is basically all the time that we have. And I wanted to say thank you to Linda and thank you to Todd for joining us today to take your questions on Voyager. And so for all of you at home, if you want to follow Voyager's journey on social media, you can follow at NASA JPL and at NASA Voyager. And so to kind of take us out, because you know Voyager took so many beautiful images of our solar system, we have a montage of images for you from the Voyager journey to the outer planets. And so enjoy this space odyssey.